Hello, we will continue with discussing acid-base concepts from chapter 18. In this video, we are going to focus on Ka and Kb of conjugate acid-base pairs. So we have previously discussed acid-base pairs or conjugate acid-base pairs as follows. So let's say we have some acid, Ha. Okay, so this is its conjugate acid form. And so then its conjugate base form would be A minus. So note the conjugate base of HA is A minus, and we get that by removing, by removing an H plus. Okay, conjugate acid, and the conjugate base. And then going in the opposite direction, if we want to see the conjugate acid of some base, like A minus, then we would add H plus to the structure. So this is a conjugate acid-base pair. Okay, we could do the same thing for some base and its conjugate acid. So again, we could start with our base here, and then the acid form would be right here, HB plus. Okay, so there's multiple ways to look at this. One of the things we want to look at next is the fact that, well, two things actually. One, let's look at the reaction, let's look at the Ka for some acid, and then let's look at the Kb of its conjugate base form. So let's say we've got some acid Ha, and if it reacts with water, we will form its conjugate base A minus, and we will form H3O plus. Okay, and actually I'll put the H3O plus in black this time because we want to focus on the conjugate acid-base pair. Let me redraw the arrows here. Okay, aqueous, liquid, aqueous as previous. So Ka then for this is going to equal the concentration of A minus times the concentration of H3O plus divided by the concentration of HA. If we take that same conjugate base and we react that with water to reform its acid form, and thus leaving behind OH minus, then this would of course be a Kb expression since water is ionizing, and we're adding a proton to the base, forming OH minus. And so then that's going to look like HA times OH minus concentration all over the A minus concentration. Okay. Now, what I want to show you here is if we add these reactions together, then what we get, well, first of all, the HAs will cancel and the A minuses will cancel. And what we get is 2H2O in equilibrium with, H3O plus and OH minus. And so remember, as we learned in the previous chapter, K total is going to equal the multiplication of the K values. Okay. And so what we would get is, again, cancel, cancel, and we get concentration of H3O plus at equilibrium times the concentration of OH minus at equilibrium, which is just KW. Okay? And so what this tells us then is for any conjugate or for any acid. So let's say, for example, we've got the acid HC2H3O2, and it has a Ka value of 1.8 times 10 to the negative fifth. And let's say we want to know the Kb of its base form, C2H3O2 minus. Well, what would that be? Well, as we just said, Kw is going to equal Ka times Kb. And if you'll remember, at 25 degrees Celsius, Kw is 1.0 times 10 to the negative 14th. And so if we do that work here, we would take 1 times 10 to the negative 14th, and we would divide it by our Ka, 1.8 times 10 to the negative fifth, and we get a final answer of 5.6 times 10 to the negative 10th. If we multiply those together, we get our 1 times 10 to the negative 14th back. Now, this tells us something very important about conjugate acid-base pairs, right? For any acid, the better and thus stronger the acid form is, the worse and thus weaker its base form is. There's an inverse relationship, okay? A strong acid will have a weak conjugate base. A weak acid will have a strong conjugate base. The stronger the acid, the weaker the base, right? So for example, Ka of HCl is greater than 1. In fact, it's very, very difficult to measure because this is a strong acid, right? Remember, these up here, better, weak acid, worse, weak base, okay? But in this case, this is one of our strong acids, right? It's immeasurably strong in water, and we're going to talk about that in another video. So that means the conjugate base of HCl, which is Cl minus, will be very, 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 very small, right? Because if Kw equals 1.0 times 10 to the negative 14th, well, then 1 times 10 to the negative 14th divided by a very large number will lead to a very, very small number. And so we end up with something that's much, much less than 1.0 times 10 to the negative 14th. I'll just call it an ultra weak base, right? In fact, remember, HCl is such a strong acid that when we write this reaction, we don't write a double arrow as if it is an equilibrium. And effectively, 0% of this is left in solution and 100% gets converted to Cl minus and H3O plus. So that means if it's 100% ionization effectively in the forward direction, then in the reverse direction, it is effectively 0. Okay? So this is the relationship between conjugate acids and bases. Now we can use this information in scenarios, because remember, Ka is with respect to water, and Kb is measured with respect to water, right? And so in the case of a Ka, water is acting as the base for that reaction. And in the case of a Kb, water is acting as the acid. So we're using water as our reference. But what if we have stronger acids and bases than water in the same solution? So let's say, for example, we have the acid H2S aqueous plus we have the base NH3, okay? And that would form the base HS minus aqueous, that should be aqueous, and then the acid NH4 plus aqueous, okay? Now note, all of these are stronger than water, okay? All of these are stronger than water. So note, we could look up our Ka for H2S, our Ka for NH4 plus, and we can look up our Kb for NH3 and our Kb for HS minus. But all of these will have Ka and Kb values higher than that of water, okay? Because it turns out the Ka for water, as we're going to see, is 1.0 times 10 to the negative 14th. And the Kb for water, so remember, that's just water reacting with water, is also 1.0 times 10 to the negative 14th. Okay, because writing the Ka or the Kb reaction for water is just Kw. Okay, so water is, and by the way, so that also means that the Ka of H3O plus is 1, and the Kb of OH minus is 1. Okay, so those are the strongest acid and base in water. Again, we'll talk about that in a future video. So based on this, where would we predict the K to be for this, right? So our question is K going to be approximately equal to 1? Is K going to be greater than 1? So product favored. Or is K going to be less than 1? Reactant favored. Well, let's look. Okay. Oh, let's calculate these values. Okay, so we have H2S, and that is a value of 1.0 times 10 to the negative 7th. Okay, that's hydrogen sulfide. And so it's, here, let me switch these here. That way the pairs are on the same line. Let's look at the Kb for its conjugate base form, and we could calculate that. It's also going to be 1.0 times 10 to the negative 7th, right? Because remember, Ka times Kb for an acid conjugate acid base pair must always multiply to give 1 times 10 to the negative 14th in water at 25 degrees Celsius, right? So now let's look at NH3. That is 1.6 times 10 to the negative 5th. Or sorry, 1.8 times 10 to the negative 5th. Try that again. 1.8 times 10 to the negative 5th. And that means its conjugate acid form would be 5.6 times 10 to the negative 10th. And so to figure out which side this is going to lean on, we need to figure out which acid is stronger, and we need to figure out which base is stronger. Okay, so if we look here, we can see that this number is bigger. 1 times 10 to the negative 7th is bigger than 5.6 times 10 to the negative 10th. So this is the stronger acid versus NH4 plus, which is the weaker acid. In other words, if they both get a chance to put a proton in water, H2S does a better job of it. Okay. If we look at the bases, we can see that NH3 is the stronger base because it has a higher Kb value, and that means HS minus is the weaker base. Okay, and so now how does this help us with figuring out where the equilibrium is going to lie? Well, the favored side, so this reaction, sorry, this equilibrium will favor the side with the weaker acid and base, which would be this side. So that means that this reaction would be product favored. Okay, so overall, if we looked at this, the concentration of HS minus and NH4 plus are going to be higher, and the concentrations of NH3 and H2S are going to be smaller. Okay, so this is how we compare, this is how we determine the net direction of the equilibrium. Okay, so again, and again, it is the stronger acid is going to react with the stronger base. So NH3 and HS minus would both be present, but H2S would rather give its proton to the stronger base, NH3. Okay, and so they are much more reactive with one another than NH4 plus and HS minus are with one another, and thus there will be more of HS minus and NH4 plus in solution at equilibrium. Since they are on the product side, this is a product favored equilibrium. Okay, so that concludes discussion of Ka, Kb, conjugate pairs, and net reaction of a direction. And so note, by the way, this little trick here, right? So here, let's go back here. Let's go back. So I guess I'll write it off to the side here. So note that Ka times Kb, so this is just a reminder, for a conjugate acid-base pair will equal Kw, which is 1.0 times 10 to the negative 14th. That also means that the pKa of an acid and the pKb of its conjugate base will equal pKw, which is 14.00. Note 2 sig figs, and thus 2 decimal places in this value, right? Okay, so that's kind of the takeaway of this little section. I will see you in the next video.